When the Chandra X-ray Observatory was launched aboard the Space Shuttle Columbia on July 23, 1999, it began a new era of X-ray astronomy.
4, 3, we have a go for engine start, 0. We have booster ignition and liftoff of Columbia, reaching new heights for women in X-ray astronomy.
But what do X-rays from space tell us? And why do we build telescopes to study them? Most people think of light as what we can see with our human eyes. But in truth, our eyes can detect just a small fraction of the radiation emitted by objects in space. Martin Elvis, a senior scientist at the Chandra X-ray Center in Cambridge, Massachusetts, discusses why astronomers want to study the sky in X-ray light.
So, what's X-ray astronomy? You look up at the night sky and you see stars all over the place. Stars like our own sun, big ones, small ones, old ones, young ones. Basically, all stars shining with fusion power, nuclear fusion. We only see stars as dominating the night sky because we look in this really narrow band of the whole electromagnetic spectrum called the optical range. If you look well outside this range, either at long wavelength or short wavelengths, you don't see the same stars at all. So we tend to talk about X-ray sources, and they're really not stars. The sky in X-rays is not dominated by stars. Instead, it's dominated by something entirely different that's powered not by nuclear fusion, but by another process which is many times more efficient at converting mass into radiation than nuclear fusion is. Since nuclear fusion is the most efficient process we have around us on Earth, that's pretty impressive. So X-ray astronomy in one sense is just trying to answer the question, what is this stuff? When we look at the sky in X-rays, what do we see? And it's something entirely new, something you would never have guessed just by looking up at the night sky.
One of the most exciting things about X-ray astronomy is that it's really in its infancy. The first X-ray satellites weren't launched until the 1960s. Why the late start? The answer is because X-rays from space are absorbed by the Earth's atmosphere. Therefore, X-ray astronomy had to wait for the space age and the development of rockets to get its detectors into orbit. And what does Chandra see in the X-ray universe? When matter is heated to really high temperatures, as in millions of degrees, X-rays are produced. Here's more from Martin.
The energy of each photon of light in X-rays is about 1,000 times that in optical light, visible light. So it also follows that the temperatures that we deal with in X-rays are about 1,000 times hotter. So you're looking for processes that are 1,000 times more energetic.
So, in order to understand what is happening in the hot, turbulent regions of space, we need to have X-ray telescopes. Chandra is using its powerful telescope to study such things as material around black holes, the debris from exploded stars, and hot gas that pervades the space between the galaxies. These are phenomena and objects that would simply be invisible in other wavelengths. NASA's Chandra X-ray Observatory, in orbit since 1999, studies the high-energy universe where black holes, exploded stars, and mysterious matter hold sway. X-ray telescopes like Chandra are not like telescopes you find in backyards or at the local observatory. In addition to being above the Earth's atmosphere, they need to have special mirrors to detect the X-rays that pass through most objects. Let's listen to scientist Martin Elvis explain more about Chandra's technology.
The main thing Chandra does is take these superb, sharp images. How does it do that? Well, X-ray telescopes are different from optical telescopes. They have a very different shape. Although in fact, they're really reflecting light in just the same way as optical light. It's just that with X-rays, you have to coax them into being reflected. If you have a normal mirror, you look at yourself in the mirror and the light's going in and straight back, so it's being bounced through 180 degrees. If you try that with X-rays, they just get absorbed. But you can get specular reflection if you come into a grazing angle of a degree or less. Once you get that specular reflection, X-rays act just like optical light. You can concentrate them and focus them, no problem. Trouble is, you're only bending the light through 1 degree on each reflection. We end up having 2 reflections in our mirrors. That means that the light's only coming together very, very slowly, so we tend to have very long telescopes, most of it being just empty space. We're just waiting for the light to converge down to its focus. The bad thing about these mirrors is you're looking almost edge or end on at a cylinder, so the area of glass that the light's reflecting off is only a thin annulus. So what we do is pile a whole bunch of telescopes nested one inside the other to build up the area. But basically you still have to polish 100 times as much glass as you would for a normal optical telescope. So this 1.2 meter diameter Chandra mirror is focusing light down onto an exquisite point just 1,000th of an inch across. That's why Chandra's powerful.
In addition to its special mirrors, Chandra also travels in an unusual orbit around the Earth. Unlike its partner mission, the Hubble Space Telescope, Chandra cannot be serviced by astronauts. That's because it does not circle relatively closely to Earth as Hubble does. Martin explains more about why Chandra travels in unusual circles, or, more accurately, ellipses.
Chandra doesn't just go above the atmosphere, it goes a third of the way to the moon, getting well away from the Earth. But can't get above the atmosphere twice, so why do we bother? The answer is to be much more efficient at observing. It's only a small telescope and we tend to have to observe a long time. But if we're down where the space station is, or the shuttle can get to, then wherever you want to look, half the time the Earth is in the way. Not what you want if you're looking with an X-ray telescope. So instead, if you can afford the energy to push you way out there, the Earth looks very small, and you can point almost anywhere without it getting in the way. That's very useful for many observations, but mainly it doubles the efficiency of Chandra.
Now that we've heard a little about how Chandra works, let's listen to Martin give us an introduction to how X-rays are produced in the universe.
There are 3 different ways you can get matter to be that hot. One is simply an explosion, like a supernova, such as the one in 1987 in the Large Magellanic Cloud. What we see there is very fast-moving gas that's hit material on the outside and is now glowing with a shock at a few million degrees. The next way you can make X-rays is a more complicated process, and that's by having very fast-moving charged particles in a magnetic field. Basic law of physics is that any charged particle moving in a magnetic field gets swirled around, and in doing so it's accelerating around a bend, and accelerating charge radiates. It turns out there are lots of places in the universe where we get magnetic fields and very fast-moving, we call them relativistic, particles. They're moving very close to the speed of light. The Crab Nebula, for instance, is powered by a pulsar at the center, which has so much energy in it that the little wisps and things you see in the image, which look like they're sort of swirling around the nebula, they aren't swirling at all, they're moving outwards at extraordinary velocities. This type of X-ray making mechanism we find very commonly also in quasars and blazars, which are things with these huge jets that come out, maybe many times the size of a whole galaxy, and these are powered in X-rays by the same mechanism. The third way of making X-rays is perhaps the least likely. It's just dropping something down a hole. If you have a lot of mass somewhere, like a planet, or better still a neutron star or a black hole, and you drop something in, then it speeds up, and when it hits the surface or some other gas coming from a different direction, it heats up. A spaceship re-entering the Earth's atmosphere does the same thing. It starts glowing very hot. The spacecraft is generating heat through friction with the air and slowing down. And that's just transferring the energy of its motion into heat. So it's a very simple process, really. It just turns out that most of the X-ray sources in the sky are powered this way.
It's time to explore how the Chandra X-ray Observatory fits into the modern astronomer's toolkit. As you may know, Chandra is one of NASA's so-called Great Observatories. The Great Observatories were 4 missions selected by NASA to explore different types of radiation and really tackle the biggest questions in astronomy. The first to launch in 1990 was easily the best known, the Hubble Space Telescope, which looks at optical and infrared light. The next was the Compton Gamma Ray Observatory in 1991, which, as the name suggests, studied gamma rays, the most energetic particles known. Next up was our favorite X-ray telescope, the Chandra X-ray Observatory, in 1999, and finally, the infrared-seeking Spitzer Space Telescope in 2003. Now, for a little more perspective on Chandra's significance for X-ray astronomy, let's turn once again to scientist Martin Elvis.
Chandra takes us to the Space Telescope era just 40 years after the birth of X-ray astronomy. That's a tenth of the time between Galileo's first telescopes and Hubble. The problem for optical astronomers was the wobbling of the Earth's atmosphere, which means you don't win by making bigger telescopes. So for about 200 or 250 years, they were stuck. It took Hubble Space Telescope getting above the atmosphere to get away from that wobbliness and make images that were 10 times sharper, even though it's only a small telescope. X-ray astronomy can only ever be done from above the atmosphere. Our problem instead was that X-ray mirrors are really hard to make. And with Chandra, X-ray astronomy has gone far beyond Galileo, almost up to a space telescope level of image clarity. There have been mysteries that have been lying around for 20 years, some of them 40 years, that weren't understood until Chandra went up. And now it's like, oh yeah, now I get it, that's the answer. Or, ha, yes, that's what I thought. Yes, the X-ray background that Giacconi first discovered is made up of millions and millions of quasars at quite large distances from us. Or, another example, you can work out how much normal matter there is, not dark matter or dark energy, but real stuff we know about, atoms. In fact, if you look at very distant quasars, you can see in their light absorption by lots of little gas clouds, which add up to be just that amount of normal matter. But as you get closer towards us, half of that gas disappears. So where did it all go? That's called the missing baryons problem, and it's been around for quite a long time. Chandra solved it. Turns out the gas got heated up to X-ray temperatures, and we're sitting in a hot bath of that stuff in our Milky Way. It's a hot bath that spreads all the way to the Andromeda galaxy. And just now we found evidence for the first time of the same kind of gas further away in true intergalactic space where there are no galaxies that we know about.
Humanity has long sought to learn about the Milky Way, our home galaxy. Even after the advent of optical telescopes, the Milky Way's center, some 26,000 light-years from Earth, remained mysterious because gas and dust blocks most visible light along our line of sight. Fortunately, X-ray telescopes, like NASA's Chandra X-ray Observatory, can detect higher energy radiation that penetrates this veil of galactic debris. Dr. Frederick K. Baganoff of the Massachusetts Institute of Technology has been using Chandra to study our galactic center for several years. He explains why X-ray telescopes like Chandra are so crucial for this pursuit.
X-rays are important for studying the center of our galaxy because the Milky Way, our galaxy, is a spiral galaxy. And that means it has this sort of frisbee-shaped disk and then a bulge in the center. And in the disk are lots of dust clouds. Because our sun is in the disk, we have to look through these dust clouds to see towards the center of our galaxy. And the dust acts like smog and it blocks our view. So we actually can't see the center of our own galaxy in optical light or ultraviolet light. You can only look at longer wavelengths like radio and infrared, or the shorter wavelengths like X-rays and gamma rays.
What does Chandra see when it looks at the heart of the galaxy? It finds a sea of hot gas enveloping thousands of white dwarfs, neutron stars, and black holes. Chandra also finds regions aglow with the light of massive young stars. And that's not all. At the very core of the Milky Way lies a supermassive black hole that has a mass of nearly 4 million suns. This black hole is named Sagittarius A star, or Sag A star for short, due to its location in the direction of the constellation of Sagittarius. Sag A star is continually growing as it pulls in gas. Infalling gas is heated to millions of degrees and gives off X-rays, which have been detected by Chandra. Sometimes gas outside the black hole can become superheated and expelled from the region at millions of miles per hour. Fred Baganoff explains how Chandra has been used to observe Sag A star as it erupts into flares.
We looked at Sag A star with Chandra in the first year, and we saw pretty much just this quiescent level of emission. It was a low, steady source. And the next year, in 2000, we looked again. All of a sudden, in an hour and a half, it increases by a factor of 45 in X-ray luminosity. And then in 10 minutes, it dropped by a factor of 5. We were able to use the fact that it dropped by a factor of 5 in 10 minutes with the fact that the speed of light is constant to figure out the size of the region that it was emitting these flares. And the size of the region is about 10 times the radius of the event horizon of the black hole, the event horizon being the point at which even light can escape. So this X-ray flare was coming from a region only about 10 times that size, and that would be equivalent to about the Earth's orbit around the Sun. That small of a region was producing all of this energy.
What do scientists think caused these outbursts from Sag A star?
There are two possibilities. One is that a lot of extra mass was suddenly just dumped on to the accretion region. Second hypothesis is that it's more like a solar flare. Solar flares are related to magnetic fields, and so the second possibility is these X-ray flares were produced due to magnetic energy being turned into acceleration of particles.
Clearly, there is much to explore and learn about our home galaxy, the Milky Way, and Chandra will continue to be an important tool in that effort. Supernovas are the remnants of catastrophic explosions, and they are among the favorite targets of scientists who use Chandra. For good reason, too. Supernovas and their remnants have proven to be extremely important in understanding topics ranging from the birth of our solar system to the history and composition of the universe itself. They can help astronomers understand the origin of the elements that are necessary for life. They can be used as cosmic laboratories for studying extreme physics, and they also serve as distant lighthouses that tell us about the accelerating expansion of the universe. Dr. Patrick Slane of the Chandra X-ray Center explains why he's interested in studying supernovas.
When I took my first astronomy class in college, the thing that fascinated me the most was how massive stars evolve. They're the ultimate picture of life in the fast lane. They burn bright, use up all their resources in a stellar blink of an eye, and end their lives in a massive collapse. But they do go out with a bang. They leave their mark too. They take simple hydrogen and helium, turn them into heavier, more complex elements, and distribute them out into space, where new stellar systems enriched with these elements can form. The oxygen we breathe, the calcium in our bones, the iron in our blood were all provided in the demise of earlier massive stars. Who can resist a story like that?
But how are supernovas created? Pat Slane explains what happens before the supernova during the typical lifetime of a star.
All stars are actually destined for collapse. Stars form when gravity pulls large masses of gas together. The gravity pulls the gas inward toward the center and heats it up. This makes the gas radiate, which means it loses energy. If you can put energy into the gas, you could push it apart, fighting the gravity. But when energy is lost due to radiation, the opposite happens. It collapses even more. It's a vicious cycle that would cause the gas to compress itself indefinitely if it weren't for the fact that eventually the temperature becomes high enough to ignite nuclear fusion. This produces a high pressure inside the star that can hold off the gravitational collapse, at least temporarily.
Let's hear what happens when that star's life comes to a close.
When hydrogen runs out, this ignites a new fusion process, converting the helium into heavier elements. If the star is about 8 or more times as massive as the Sun, this process of fusion, fuel depletion, collapse, new fusion continues itself until the core is composed of vaporized iron at a temperature of several billions of degrees. But the process of iron fusion doesn't produce energy, it uses it. That means that from this point on, there's nothing to stop the crushing weight of the star. In less than a second, the entire core collapses, compressing the very center and triggering a massive explosion in which all but the very core of the star is blown out into space. These explosions, supernova explosions, are the most violent events in the universe.
But a star's story does not end with its fatal collapse. Instead, a star's death can be a transformation as its stellar ashes are recycled into the space around it. A supernova is the explosive death of a star. As one of the most energetic events in the universe, a supernova may temporarily outshine the rest of the galaxy in which it resides. But what are supernovas? Every 50 years or so, a massive star in our galaxy blows itself apart in what astronomers call a supernova. Supernovas are some of the most violent events in the universe. The force of the explosion generates an intense flash of radiation, as well as shock waves analogous to sonic booms. These supernovae are often best seen through X-ray telescopes like Chandra. Dr. Patrick Slane of the Chandra X-ray Center talks about supernovas in our own galaxy.
In our own galaxy, these types of supernova explosions occur every 50 years or so. The explosions pound the nuclei of atoms together so violently that they build up all the heavier elements of the periodic table. These are flung out into space where eventually they mix with other interstellar gas and form new stars and planetary systems enriched with these heavy elements. Although our galaxy seems to be in somewhat of a drought for supernova explosions, with the last one being observed in 1604, we see the remnants of these explosions all over the place. The outgoing blast wave from the explosion sweeps up the interstellar gas and heats it to temperatures so high that they glow in X-rays. They can be 40 or 50 light years across, and for the youngest ones, we can actually still see them expanding.
Pat Slane explains how one kind of supernova, called Type 1a, works.
Many stars are formed in binary systems. After one star in the system evolves into a white dwarf, it's possible for the companion star to approach the end of its life, in which the hot interior causes the outer layers to expand. If they expand enough, some of the gas can fall over onto the white dwarf. This transfer of matter onto the dense white dwarf can eventually increase its central temperature enough to detonate the entire compact star in what's called a Type 1a supernova explosion. Here, the entire white dwarf star is obliterated. This type of supernova always produces about the same brightness, unlike supernova explosions of massive stars, which can vary a lot depending upon the mass of the star. These Type 1a explosions can be seen in other galaxies out to incredible distances. In fact, they provided the first evidence that the most distant objects are moving away from us more rapidly than expected, the result of dark energy accelerating the expansion of the universe.
X-ray telescopes, particularly Chandra, are very important tools for astronomers to study supernovas. The supernova explosion is incredibly energetic and can heat any gas that surrounds it to millions of degrees. The debris field and high-energy particles within it are what astronomers refer to as a supernova remnant. Such remnants are known to produce intense X-ray radiation that can last for thousands of years. Pat Slant explains how Chandra's images are used to analyze the debris field and reconstruct the star's explosion.
Because the gas in supernova remnants is so hot, it radiates in X-rays. By measuring the spectrum of the X-rays, that is, the energies of the different X-rays that come from the remnant, we can tell how hot the gas is and what it's composed of. This lets us identify the heavy elements that were produced in the star and its explosion, and compare these with our theoretical models of how these explosions occur.
Scientists think that supernovas can trigger star formation and probably led to the formation of our very own solar system some 5 billion years ago. This supernova also likely seeded the cloud with elements like carbon, nitrogen, and oxygen that eventually went into the sun, planets, and ultimately us. These elements are manufactured deep in the interior of massive stars and would, for the most part, remain there if not for the cataclysmic supernova explosions. For these reasons that are very close to home, and to others ranging to the quest to understand the history of the universe, Chandra will continue to study these fascinating objects we call supernovas. Did you know that galaxies don't like to be alone? It's not that galaxies feel a social need to congregate with others. Rather, it's their gravitational pull, even across the vast distances of space, that can cause galaxies to form clusters that can contain hundreds or even thousands of individual galaxies. Clusters of galaxies are, in fact, the largest structures in the universe that are held together by gravity. Because of their immense size and mass, galaxy clusters are extremely useful as tools to probe a variety of questions about the universe as a whole, as well as properties of the clusters themselves. Dr. Christine Jones of the Chandra X-ray Center discusses the importance of galaxy clusters and the wide range of astrophysical topics they can address.
Since clusters are so large and so massive, they're a great place to take an inventory of the mass in the universe. In particular, how much is luminous matter and how much is dark matter. We also can study the individual galaxies in clusters and learn what kind of galaxies live in different environments, and how the galaxies, which are often moving in the cluster at speeds of 1,000 kilometers a second, interact both with each other and with the cluster gas. In addition to being massive, clusters are so luminous that they can be observed back to when the universe was only half its present age. Comparing the properties of distant clusters with nearby ones allows us to see both how clusters grow over time as smaller clusters fall into them, and also lets us constrain important cosmological parameters.
While galaxy clusters are indeed comprised of individual galaxies, that is not their entire story. That's because these clusters are filled with colossal clouds of hot gas. These clouds have temperatures as high as 100 million degrees and much more mass than all of the stars in the galaxies in the cluster. Because this gas is so hot, the only way to observe it is through X-ray telescopes like the Chandra X-ray Observatory.
One of the incredible insights we've seen with Chandra is the impact that outbursts from a supermassive black hole at the center of the central galaxy in some clusters has had on the gas in the cluster. In several dozen clusters, we've now seen X-ray cavities, some with sizes larger than the entire Milky Way, where expanding radio lobes from the black hole have pushed the hot gas out of these regions. The energy in these outbursts is enormous, more than billions of supernovae. In a few clusters, we've also seen shocks in the gas that are produced by these outbursts. With these Chandra observations, we can measure how much energy has come out since the outburst began, how long the outburst lasted, and how often these outbursts occur.
One of the most important questions galaxy clusters can help astronomers address is concerning dark matter. Dark matter is an unknown substance that comprises 90% of all the matter in the universe. Using Chandra and optical telescopes, scientists have been able to find direct proof of the existence of dark matter for the first time.
In clusters, as in the universe, most of the mass appears to be in the form of dark matter. But while we can't directly see where the dark matter is, we can determine how much there is and where it is. One of the best examples of a merging cluster is one we call the bullet cluster. Most of the gas in this subcluster has been stripped off and pushed back from the subcluster galaxies. So the question is, where's the dark matter? Some alternative theories of gravity have suggested that gravity behaves differently on large scales, and that in clusters, the hot gas alone might be enough to provide the gravity. What we found for the bullet cluster was that observations of distant galaxies behind the cluster showed that their light was distorted into arcs by the dark matter in the cluster. These observations showed that the dark matter was concentrated into two regions, one on the large primary cluster and a second at the front of the bullet. Since the X-ray gas is no longer at the front of the bullet where the dark matter is, the gas can't be making up the dark matter. So while we still don't know what does make up the dark matter, we know it's not the gas and must be something different that interacts much less than the gas does.
Galaxy clusters are proving to be some of the most fascinating structures in the universe. Their mind-boggling size makes them incredibly important objects to understand. Scientists have made important progress in learning about galaxy clusters, but many more questions and mysteries have emerged. This will keep these objects at the forefront of astrophysical research for years to come. For more information about the Chandra X-ray Observatory, visit our website at chandra.harvard.edu.
This was a production of the Chandra X-ray Center, Cambridge, Massachusetts. NASA's Marshall Space Flight Center manages the Chandra program. The Smithsonian Astrophysical Observatory controls science and flight operations from the Chandra X-ray Center.